Okay, so let's talk about nuclear energy in a little more detail. You should have watched a couple of videos on Play Pause It on Schoology talking about the pros and cons of nuclear energy and what exactly it is. And there's also a couple of things about nuclear accidents, so we'll talk about them in a little more detail. I'm not giving you guided notes. I am going to put the presentation online for you to look at if you need to get any notes from that. So let's compare coal versus nuclear. Coal is a domestic fuel. We can get it here in the United States. Coal is only used by burning, combustion, and when you burn coal, you give off carbon dioxide, sulfites, nitrites, particulates, which is dust, and mercury, which is very toxic. Nuclear power, it's also a domestic fuel. No combustion, nothing is burning in nuclear energy. There's no air pollution released in ideal situations. Mining, processing, transporting the fuel does create some carbon dioxide, but there's none produced during the use of the fuel. The waste products, however, are highly dangerous. There is a risk of nuclear accident, and nuclear accidents can be severely dangerous. Okay, so let's talk about how nuclear power plants work. So currently, the only nuclear power plants we have are fission reactions. In fission, an atomic nucleus is split, which releases energy. And actually what happens is some of the mass from that nucleus is actually converted directly into energy. This is a very efficient reaction. If you were to convert all of the matter in a penny into energy, you could destroy a city. I mean, it's a lot of energy. So what happens in nuclear fission is you have a chain reaction. So you break one atomic nuclei, and the particles that are produced there can break new nuclei. So you have a chain reaction going. And you can see that here in the animation. Here's a nuclear power plant. We talked about this a little bit before. You have the nuclear fuel. You have control rods that go down and absorb some of those neutrons to slow down the reaction. You can lift them or lower them to control the speed of the reaction. You have a fluid that goes and heats water, which is converted to steam. The steam turns a turbine and is then cooled and returned back into the system. So the water that is being heated and converted to steam is never released from the plant. You will see a lot of steam coming up from nuclear power plants, but this is from the coolant water. This water flows through and is converted to steam and is released, but it never actually comes in contact with anything that was in the reactor. So under normal circumstances, there's no radiation released at all. The only thing that actually comes in contact with the radiation is the fluid in the reactor, and it goes through here. This fluid is fairly close to it, and it's converted to steam, but it's also cooled and used again. So this is a closed system. The only thing that enters and exits is this cooling water that flows in and out, but it is never actually in contact with the radioactive materials. So something we'll talk about a little bit more, the reactor is in the reactor vessel, and this is a very strong structure. It has a containment shell. And we'll talk about later in accidents, if the nuclear material gets too hot and melts down, it cannot escape from this containment shell in ideal circumstances. You don't want it to escape the containment shell. So modern nuclear power plants, even in an accident, the nuclear fuel never leaves the containment shell. And ideally, this doesn't always happen, but ideally no nuclear material will be released in an accident. If you have a meltdown, the melted reactor shouldn't get any further down than here. We'll talk about meltdowns more later. Okay, so in nuclear reactors, the fuel is usually 97% uranium-238, about 3% uranium-235, and the control rods can go in and out and control they absorb neutrons to control the reaction. Here's a picture of a typical nuclear power plant. This one is in South Texas. My wife grew up very near to this plant. And you can see this is the cooling pond. It's a huge pond. The water is taken in on one side and put out on the other, and then it flows through this huge area and has lots of time to cool off before it goes back into the reactor to cool the to go work again. So it has a lot of time to cool off before it gets back in. And interestingly enough, there's a lot of wildlife in this area. Bald eagles, other types of animals. People aren't allowed to do much in this area, so this is a very, wildlife likes it a lot. Here's a picture of the core and the fuel rod assembly. There's the fuel rods. Okay, so let's talk about the dangers of radiation. I'm not sure why that keeps coming up. Okay, the dose makes the poison. So, background radiation, every day you're getting 0.1 to 0.2 per year. REMS, 0.1 to 0.2 REMS per year. If you get an X-ray, that's 1 REM. So that's several times higher than that, but it's not harmful, and as long as you're not getting an X-ray several times a day or anything. The upper limit for safety is to get 5 REMS per year. If your job exposes you to more than 5 REMS per year, they're going to have to change something. Okay, 10 REMS in an incident. If you get exposed to 10 REMS at once, if you're pregnant, that can cause embryo abnormalities. 100 REMS all at once is probably going to cause leukemia. 1,000 will cause nausea, harm to the intestines, and you will die in 2 weeks. 10,000, coma and death in 2 days. 100,000 will kill you right on the spot. So this shows you where the reactors are in the United States right now, and I had to change, I got the base of this PowerPoint off the internet, and I had to change this because several have been closed down. At the moment, we have 98 reactors at 60 sites in the United States. And you can see New Mexico doesn't have any. The closest to us are in Arizona and Texas. And there's a lot on the East Coast. Midwest has quite a few. Few in California and Washington. Okay, so the big problem with nuclear energy is the waste. There's 2 types, low level and high level. Low level waste, well, we'll talk about that more in a second. Yeah, you have low level waste and high level waste. Low level waste is bad, but it's manageable. High level waste is the kind that you have to deal with for tens of thousands of years. Okay, so low level waste. This is things like protective gear that was used in radiation places where it can be exposed to radiation. You don't just throw that away. It's got radiation. It's radioactive now. X-ray waste, X-ray machines, and there's thousands of those across the country. They produce waste that are radioactive. Medical waste, this is talking about things like radiation treatment for cancers and that type of thing. These are stored in near-surface waste facilities, and they remain radioactive for about 100 years, which sounds pretty bad, but this is not near as bad as what we'll talk about later. Here's just an example in 2010 of the radioactive material locations in Texas. And you can see there's a lot of it all over the place. High levels are the red, and there's a lot in the Houston area up here. Significant moderates are scattered around. To manage low-level waste, what they do is they seal them in these containers, and then they bury them. They have a clay area. Clay, it's impermeable to water. Barrels are stacked. They're surrounded by sand, buried in sand, covered up, and sealed off. So in the end, you're going to have grass and topsoil and gravel, a lot of soil, compacted clay, Then you have your sand and your materials on top of gravel and clay, more clay. What a lot of people worry about is the transport of these materials, because you're carrying them by a truck, and if there's an accident, that's when you can have problems. If you have one of these rupture on the middle of a highway. While I was doing some research, I found a couple of people died in Russia. They were hunting and they found some metal cylinders lying in the road, and they had melted all the snow, and so they were hunting and camping, so they slept next to these to stay warm, and it was actually radioactive waste that had fallen off of a truck in Russia and was laying on the road, and those people didn't know it was radioactive and they died. Okay, so this is Andrews County, Texas. It accepts waste from 36 states. This is low-level waste, remember, and you can see the cranes, so this is a pretty large area. Something else people worry about is having this stuff just lying around is dirty bombs. You don't hear about it in the news as much, but there's a fear that terrorists could get some of this stuff, put it in a bomb in a city, and blow it up. And there's no nuclear explosion, but there's a lot of radioactive stuff spread all over the city and could cause lots of problems. So security is an issue with some of these open sites. Just real quickly, this shows different states have come together and they gather their stuff, all their waste, and put them in one or two sites, low-level waste. So these are the states that gather ours. I couldn't find where we put it, but it doesn't seem to be in New Mexico. And you can see the Northwest all get together. They store theirs in two places here. The second kind is high-level waste. This stuff can be radioactive for tens of thousands of years. This could be spent fuel rods from nuclear reactors. It could be stuff that was used in making nuclear weapons, or when they decommission nuclear weapons. That stuff is dangerous for tens of thousands of years. And here you can see where this is stored. And we actually have quite a bit of it in New Mexico. Some of this is from nuclear weapons development around Los Alamos and places like that. The triangles here are Department of Energy owned spent nuclear fuel and high-level radioactive waste. The blue is non-Department of Energy, so that's probably going to be weapons types. And as you can see, we have quite a bit of it in New Mexico. Okay, so this is the Carlsbad Waste Isolation Pilot Plant. I want to show you this video. This is put out by Department of Energy, so it's a little bit slanted.
A bedded salt formation resulted from the evaporation of the Permian Sea. Today, that same salt formation protects our future by providing a safe place to permanently dispose of the nation's defense-related transuranic radioactive waste. Welcome to the U.S. Department of Energy's Waste Isolation Pilot Plant. WIPP is located in the desert in southeast New Mexico, far from major population centers. WIPP began disposing of transuranic, or true, waste in March of 1999. True waste generally consists of clothing, tools, equipment, sludges, soils, or other materials contaminated with man-made radioactive elements that are heavier than uranium, thus the word transuranic. Approximately 96% of the waste WIPP will receive is contact-handled true waste, meaning that the waste containers can be safely handled by workers without additional shielding. The remaining 4% will be remote-handled true waste. Remote-handled waste is shielded during transport and is handled using robotics and machinery. Congress limited the WIPP mission to defense-related true waste only. Temporary, above-ground storage of true waste poses long-term risks to health and the environment. WIPP's nearly half-mile-deep disposal rooms safely isolate these wastes from the accessible environment. True waste, now temporarily stored at DOE sites around the nation, is carefully examined to make sure the waste meets strict WIP disposal requirements. This process is called characterization. True waste is safely shipped to WIP in special transportation containers certified by the U.S. Nuclear Regulatory Commission. Remote handled waste is disposed in horizontal boreholes drilled into the walls of underground disposal rooms. Contact handled waste is stacked in columns on the disposal room floor. Over time, high pressure on the salt formation will cause the salt to creep, filling in voids of the disposal rooms and entombing the waste permanently. True waste, temporarily stored above ground, poses a potential threat to human health and the environment. WIP's mission is to isolate that waste forever.
Okay, so this is near Carlsbad, so in the southeast corner of the state. And they actually had some accidents there. And I've put some links on an assignment on Schoology for you to do some research on that. They're recovering from those accidents, but yeah, they have had some issues. So how long will this stuff remain dangerous? High-level waste is radioactive for around 10,000 years, or tens of thousands of years. These are spent fuel rods, things like that are currently stored on site at the nuclear power plants. So nuclear power plants around the country, and you saw the map where they all have radioactive waste stored on site that is dangerous for 10,000 years. So let's talk about half-lives. You've probably learned this in other classes, but if you haven't, we'll talk about it now. This is the amount of time required for half of the nuclei in a radioisotope to emit its radiation. Half-life is you talked about in some other applications as well, but we're going to be talking about it mainly with radiation. So, and this is different for the element. Potassium-42 is 12 hours, so this stuff goes away pretty quickly. Iodine-131 is 8 days. Strontium-90 is 28 years, and carbon-14 is 5,370 years. You've probably heard about carbon-14. It's generated in the atmosphere at a steady rate, and we use this to determine how old artifacts are. Up to a certain age, you can take like trees or bones that are. It doesn't work for dinosaurs. It works in the tens of thousands of years range. You can measure the ratio of carbon-14 to carbon-12 and find out how old things are. Okay, so uranium-235, 710 million years, and uranium-238, 4.5 billion years. So one half-life has gone by for uranium-238 in the life of the planet. So this is how it looks. This is a number of half-lives, and after one half-life you have half of what you had, then a quarter, and on down, so on and so forth, until you have very minuscule amounts. This isn't too bad if your half-life is hours or days, but if it's 4.5 billion years before it's all gone, you've got to wait for 8 times the life of the planet Earth. So I don't know if you'll see problems like this on the AP exam, but it's possible. So and they're pretty easy. So let's just go over how this would work. So you have iodine-131. Its half-life is 8 days. If you started with 1 kilogram, how much radioactive material would you have in 32 days? So the first thing to figure out is how many half-lives that is. My mouse has disappeared. Okay, so 8 days, so 32 divided by 8 is 4. So that's 4 half-lives. So after 8 days, you've lost half of it. So you've gone from 1 kilogram to half a kilogram. In 16 days, you would have a quarter of a kilogram, 0.25. You divide it in half again. So every half-life, you divide it in half. So in 24 days, it would be 0.125. And by 32 days, you'd have 0.0625 kilograms left. It's a fairly easy calculation. If you can figure out the number of half-lives and divide it in half each time, that's all you have to do. To figure it out for higher numbers of half-lives and things, there are mathematical formulas, but they're fairly complicated, and we're not going to go into that right now. Okay, so the way radioactive decay works, and we're just going to go over this real quickly. Uranium-238 okay, yeah, I can't point at things anymore. Tell you what, we're just going to pause this. There we go. Okay, so uranium-238, its half-life is 4.5 billion years. When it decays into another element, thorium-234. And you can see its half-life is 24.1 days, so much shorter than uranium's. Protactinium is the next one. Its half-life is a minute, so it doesn't last very long at all. But then you get to uranium-234, 245,000 years. This is a logarithmic scale, by the way, so the distances change very quickly. And you can see as you go down, the different elements that are formed, each one lasts a different amount of time. If you go all the way through the process, you end up with lead-206. So uranium decays into lead, and this lead-206 is stable. It doesn't decay anymore. So basically, the only thing you need to know about this is as it decays, you end up with lots of different things that have different half-lives. So if you've been working with uranium-238, eventually you're going to have all of these products. Most of them, thorium-234 is going to go away pretty quick. Protactinium is going to go away very quickly. Its half-life is a minute. But you're going to be left with a lot of this stuff, uranium-234, thorium-230, radium-226, all with half-lives in the thousands of years. So as it ages, some of it gets pretty safe pretty quickly, but you're left with some of these long-lived elements that cause a lot of problems. Okay, once again, here's where the nuclear reactors are. There's 98 of them in the United States right now in 60 different sites. Okay, let's talk about Yucca Mountain. This is where it is, and this is what the area looks like. This was, and I'm giving you an assignment to do some research on Yucca Mountain. This was going to be our waste depository for nuclear waste from the entire country. We spent a lot of money on developing it and built a good portion of it. And then there was enough of an outcry from the people living around there that they didn't want it there. And you see it's not too terribly far from Las Vegas. And so now it's been shut down. I don't think any material was stored there at all. And this is kind of like the one near Carlsbad. They had these shafts going down very deeply, and then the nuclear material was stored down here and buried and capped. And so this was supposed to be long-term storage for the nation's nuclear waste. People in the area didn't want this there. They were worried about earthquakes, about groundwater contamination, about just the process of having all these trucks full of nuclear waste from the entire country driving through down the roads or on the train tracks through their areas to get here. So it was eventually canceled during the Obama administration. So some alternatives to having all this storage. There are reactors that are possible that would use 99.9% of the fuels, fourth generation reactors. We haven't developed those yet. They're thinking maybe by 2030, but I always take these numbers with a grain of salt. So big need for engineers and creative thinkers to develop things like this, but they are conceivably possible. So let's talk about nuclear accidents. One nuclear accident can really ruin your whole day. And this is one of the controversies about nuclear energy is the accidents can be really severe. So here's what we're talking about, a nuclear meltdown. Because of overheating, because of some kind of failure in the plant, the reaction gets away from them. The control rods can't go down, you can't cool it one way or the other, and the nuclear material melts and it falls down to the bottom of the reactor. And you can see in this animation, it falls to the bottom of the reactor, but the reactor vessel is not breached, so the material stays in place. There were fears for a while. They called it the China syndrome. I'm not sure why. I need to do the research. But if the nuclear material was hot enough and it breached the reactor, it could actually melt down into the ground. And when it reaches the water table, the water would be vaporized, and you could have this giant explosion releasing this nuclear material. That has never happened where it sinks through the ground, but we have had several plants that have had partial or complete meltdowns. This ruins the reactor, but ideally it will not release the nuclear material. If, however, it does, usually this accident happens, there's lots of forces involved, and the container could be breached and nuclear material could be released into the air. At Chernobyl, they used graphite for their control rods, and the container was breached, air was allowed in, and once the air got in, the graphite burns, and it burnt and released radioactive material into the air. So, 3 Mile Island, this was in the United States, 1979, Pennsylvania. There's a mechanical and a human failure, so coolant water was lost in one of the reactors. It was only a partial meltdown, and there's some controversy, but most people believe very little or no nuclear material was released into the atmosphere. The site actually continued working. The reactor that melted down was not. It was decommissioned and isolated. But these two continued working until 2019, and the plant was losing money, so they actually shut it down, and the entire site is now being decommissioned, removing a lot of that radioactive material, which is high-level radioactive material, and so it has to be taken somewhere. But anyway, that was the first nuclear accident in the United States, and it put a damper on nuclear power plants. People were scared of this, so people stopped making new nuclear power plants for a while. Chernobyl. This was the worst one. In April 26, 1986, human error led to a meltdown. They were actually trying to test some things, and so they turned off some of the safety features, and they had a meltdown, and a lot of really bad things started happening. 30 immediate deaths, so just on the site, 30 people died. 116,000 people were evacuated, and an area the size of Florida was contaminated. So this was a serious issue. Cesium-137 and iodine-131 were released. Both of these are carcinogens. Iodine is picked up by the body and goes into the thyroid glands. So when you have radioactive iodine-131, thyroid cancer is a very big possibility. The thyroid cancer rates in children in Belarus, which is not too far from Chernobyl, are 100 times higher than pre-accident levels. And there's a lot of controversy about this. Different governments say different things, but the consensus outside of Russia at the moment is that eventually up to 4,000 people will probably die from Chernobyl from cancers and things like that. Radioactive particles were dumped hundreds and hundreds of miles away. So here's where the soil was contaminated after the incident. Some of the dust went long distances, and they were actually throwing milk away in places hundreds of miles away because they were afraid the cows that were grazing on grass that would have had fallout on it. And what's even worse is Russia didn't tell us about this for a while. In fact, they didn't fess up, if I remember right, until some areas quite a ways away started reading high levels of radiation and were wondering what was going on. Here's another video. I believe I've put this on your assignment, and I'm not going to play it here just to keep this video short, but I do want you to watch it. It is on Schoology.
Chernobyl is a...
Okay, Fukushima Daiichi and I probably did not pronounce that right. This is one of the most recent major nuclear accidents. This happened in 2011, not so much because of human error, but because of a tsunami. There was a really bad tsunami you've probably heard about in 2011. It caused a full meltdown in 3 reactors because of the tsunami and the earthquake. There was an inability to cool the reactor cores. Seawater was used in an emergency to keep the cores cool, which ruined the reactors. Loss of moderating fluid. Released about 1/10 of the radioactive material that Chernobyl did. This was cesium-137. Japan is still concerned about the food supply. And there's a 20-kilometer exclusion zone currently in place that people are not allowed to go into. So current status, this information is from 2014. Some residents were allowed to come home into the disaster zone. About 350 people from the district were allowed to head back to their homes. There are 31,000 people that eventually should be able to return home, they added. And in 2014, about 138,000 Fukushima, however you say that, Fukushima residents are still living in temporary accommodations. And they've declared the areas habitable if they've got no more than 20 millisieverts of radiation per year. And they would like to get it down to 1 millisievert a year. Containment effort has been wrecked by lots of problems. Regular reports of leaks of contaminated material. There's an estimated 100 metric tons of highly contaminated water that overflowed a barrier around a containment tank that's being absorbed into the ground. Plant operators, Tokyo Electric Power Company, said in a statement, though it denied there was any leakage into the Pacific Ocean. By 2022, this is in the recent news, they will have run out of space to store contaminated cooling water. They don't know what they're going to do with it after that. One plan that several people want to do is to dump it in the ocean. Their idea is that this material is not very dangerous, and the Pacific Ocean is very large and it will be diluted. Of course, the fishermen groups oppose this because even if it doesn't damage the fish, if they're right, and it doesn't hurt the fish or hurt the people that eat the fish, people are not going to want to eat fish that was taken out of areas near where this water was dumped for fear. So that's a controversy they're going to have to deal with quickly. They have millions of gallons of water that they've been using to try to keep the cores cool that is now contaminated, and it's stored there on site. Okay, so that's the end of the nuclear energy PowerPoint. Like I said, there's a couple of assignments about nuclear energy. After this, we're going to start talking about renewable energy. And nuclear energy, it's kind of a conundrum. In a lot of ways, it's very safe. If you look at the Kurzgesagt videos I've assigned for you to watch, you'll see that the accidents are bad and they contaminate large areas for a very long time. But a lot more people are killed by burning fossil fuels than are killed by nuclear power plants. And Kurzgesagt says it's kind of like focusing on airplane disasters versus car wrecks. A lot more people are killed in cars than are killed in planes, but we focus on the big disasters. So, and then there's the whole issue of waste storage. It's an issue I personally am not highly in favor of nuclear energy, but there are a lot of good things about it, and some of the bad things are overplayed. So, but in the long run, it's a non-renewable resource, and it's very dangerous to deal with, where if we can get into things like wind, solar, things like that, those don't have the issues of waste storage and all of that kind of thing, and are a lot safer, and we can't run out of it. So that's the issue, and like I said, there's a lot of pros and cons for nuclear energy. I'll let you make your own decisions. The Kurzgesagt videos do a really good job of giving the pros and the cons and letting you make your own decisions. So, But now you know, and like I said, I will post this PowerPoint online if you want to take notes from it. Stay safe.